One set of questions. Side question. Yeah, yeah. Please ask. Pardon again? I've gone through the answer yesterday. Yeah, I know you were not present. So size of the electrode, which is a solid, right? The concentration remains unchanged. So do you think it will affect the POE? Yeah. So please refer to the video on how I teach you in the organization of answer. Okay. Okay, so let's move on. So for this last part, the above electrochemical cell is dead. Okay, so basically it's telling you that the EMF is 0. Okay, so dead means EMF is 0. Or when it reaches equilibrium, it also implies that EMF must be equal to 0. All right, so the E cell will become 0 when it reaches equilibrium, in other words. Okay, so because of this criteria, right, then you have to make use of the x-intercept. So earlier on, we made use of the y-intercept, right, whereby logarithm 1 mole per dm cube of M2 plus is 0. Okay, then we make use of the y-intercept. Now we are making use of the x-intercept. Okay, whereby E cell equals 0. So from there, you are able to deduce the concentration of nickel 2 plus. Are you able to deduce the concentration of nickel 2 plus? Okay, so what's your Kc value? Do you get a Kc value? So anyone who has calculated the Kc value, sorry. Yeah, anyone who has calculated the Kc value? What happened to Kc? NSG. There's NSG today. Wait, cross country. Oh, okay, never mind. All right, so in this case, right, anyone who has a Kc value, what's your Kc value? Huh? Nobody has it. So we have, after giving you this hint, EMF must be equal to 0, right? It's as implied by the question. Are you able to get the concentration of M2 plus? Will you be able to get the concentration of M2 plus? Pardon again? So what is the Kc expression here? What is the Kc expression here for this equilibrium? Concentration of nickel 2 plus. This is your product, right? So do I need to include the M solid? No need, huh? So in this case, the reactant will be concentration of M2 plus. So that will be your Kc expression. Yeah. So using this Kc expression, and do we know the concentration of nickel 2 plus? Do we know the concentration of nickel 2 plus? What is it? What's the concentration of nickel 2 plus? Yeah, 1 mole per dm cube. So you are given in the question stem, this is the standard electrode, all right, under standard condition. So 1 mole per dm cube. Then are you able to deduce the concentration of M2 plus from the graph? Class, you should have done the tutorial. Okay, so are you able to get the answer from the graph? Oh, because they tell you that it's at equilibrium. Okay, when E cell is positive, that means it's spontaneous in the forward direction. When E cell is negative, it's spontaneous in the backward direction. So it will become 0 when both directions are at equilibrium. Yeah, so that means both directions are equally spontaneous. That's how you reach equilibrium. Okay, so this implies EMF equals 0. Can? All right. Okay. So are you able to calculate an answer? Okay, no answer from you. I'll just take it as you know how to calculate. Okay, so let's move on. Okay, so let's look at part E. Using your answer from part C and relevant data from data booklet, predict what might be observed when a rod of metal M is dipped into aqueous solution of copper 2 nitrate. So in this case, recognize that this is no longer a half cell. This is no longer a half cell. Okay, you only have the metal M without the M2 plus. So recognize that the metal M can only undergo oxidation. Correct? Metal can only undergo oxidation, right? So this metal M must appear on the right side. Okay, and the reduction potential is obtained from answer C. Okay, so this is what you should make use of from your part C. Okay, M2 plus M standard electrode potential is negative 0.13. Okay, so if your metal M can only undergo oxidation, this means that your copper 2 nitrate must undergo reduction. Agree? Yeah. So in this case, you can consider reduction of copper 2 plus. Can we consider reduction of nitrate? Can we consider reduction of nitrate? There's copper nitrate solution, right? Yeah, so can we consider reduction of nitrate? Okay, so how do we tell whether reduction of nitrate is possible or not? You quote the E0 values, right? So are you able to find the relevant half equation involving your copper 2 or your nitrate? So for nitrate, right, reduction potential, you need H plus to form your, what does it form? Your data booklet. NO2? Okay, NO2, so what's the E0 value? 0.81. Okay, so if you look at copper 2 becoming copper 0, right? That is a positive 0.34 volt. Okay, so between these two, nitrate seems to have a more positive E0 value. Doesn't mean that nitrate will be reduced. Okay, if you have chosen nitrate as your answer, right? Okay, that will be wrong, unfortunately, because to attain this 0.81 volts, you need the presence of H plus. You need the presence of H plus. Okay, so that's why in our answer key here, right, we did not even consider reduction of nitrate because acid is not present. Yeah, okay, so this is out. So you must recognize that any half equations involving H plus must have acidified medium. If not, it will not be applicable. Okay, so this one is not applicable. Okay? All right, so in other words, we are only considering reduction of copper 2 to become copper 0. Okay, so after that, after I've identified the two half equations, what do I do next? After I've identified the two half equations and I recognize that my reactants are on the opposite side of the equation, right? So that will definitely form a redox couple. Yeah. So what do I do next? Write the overall equation. But before even I write the overall equation, what must I check? Yes, we confirm that the reactants are on opposite side of the equation. One undergoes oxidation, the other one undergoes reduction. What else must we do to confirm that this reaction does take place? What must I do? Yeah, you need to calculate E cell value. Okay, so after confirming there is a redox couple, you have to calculate the E cell value to confirm that is more than 0. Then a reaction can take place. Okay, if you form a redox couple, E cell is less than 0, then your observation will be totally different. Do you get me? All right, so after forming redox, you still need to clarify, calculate the E cell to determine whether it's feasible or not in the forward direction. Okay, so this is what you're going to get. Okay, so what do you think will be the observations? Yeah, so copper metal, right, appears as a pink solid. So you should see deposition of pink solid. Okay, what else will you observe? Yes, the blue coloration due to your copper 2 plus cation, right, will decrease in intensity because your copper 2 is being used up, okay, to become copper 0. Okay. What else will you observe? Not sure. Yeah, so it depends on the packing though. So does it really coat? We are not sure. So you just say that there will be deposition of pink solid. Where it deposit, we don't care. Okay. All right. What else will you observe? What else will you observe? The metal rod will dissolve. You should see the metal rod dissolving or decreasing in size. All right. So that will be the observation. So the assumption here is your metal rod, the M2 plus is colorless. The M2 plus is colorless. Okay, so that it doesn't add any color to the solution. Okay, so that's our assumption here. All right, so that's all for the tutorial for electrochemistry. So if there's no further question, then I'll proceed to electrolytic contents. Yes? 12C. Negative value. Oh, so is this the wrong answer? For part C, do all of you have this value, negative 0.13 volt? Okay, so how do you get this value? No, because from the earlier part, you know that this is the cathode, right? Yeah, so cathode E0 cell, E cell must be, this is the standard electrode potential, right? So E0 cell will be equals to your, this is from the y-intercept. Then this is your E0 of N2 plus, which is the cathode, minus away the E0 of your nickel. So if you're using this correctly, then you should get the answer. You're using this math, this yeah. So what's the E0 cell value? So do you realize where's your mistake? Can already? Okay, all right. Okay, so let's proceed to the electrolytic part. Okay, so remember we stopped at the checkpoint. One of the checkpoint here. Checkpoint number 1, right? Is it? Now I'll not spend a long time on this topic because I feel that is quite straightforward. Okay, so what I'll do is I'll just highlight the main points. If I can finish early, I will let you off early. Yeah, okay. All right, so this is where we left off, correct? Have you completed the exercise? Do you go back and do as homework? Checkpoint 1. So should I give you 1 or 2 minutes to complete it?
Like this question. So like there's a lot of equations for water. So which one do we use? It's like a lot of equations for water. So
Understand.
how do we know which one to use?
Yeah, so you have to look at the context. So for example, water, if you're talking about cathode, then water must be on the left side. Agree?
Yes.
Yeah, so this one is one of them,
Yeah.
but this works if there is air bubble into the system. That means the context must describe in the presence of air.
Oh.
Yeah. Then yeah. So for other water, right?
Yeah, H2O.
H2O. Yeah, this one must be present also.
What's that?
I don't know. We never used this before. So this is a reactant that we won't ever use.
Okay.
Yeah. So if you are talking about oxidation of water, then your water must be on the right side. Yeah. Yeah.
Also, we use this one and not the one that is 0.4. We don't use this one because
reduction or yeah, because there's no
water is on the
oxygen.
right side.
Yeah,
Oh.
there's no oxygen.
Okay, thank you.
Yeah. So a lot of times, right, if there are other species present in the house cell, you must make sure that it's there also in the question. So do you all find it challenging to choose the right half equation involving water? If it confuses you, you must clarify with me. Maybe I just show the data booklet. Are you okay? Still working on it? Are you more or less done? Okay, for those who are done, right, I would like you to tell me, what is the biggest difference between electrochemical cell and electrolytic cell in terms of the species that we consider? Yeah, electrolysis, right, we always consider participation of water. Whereas in electrochemical cell, we seldom talk about water unless we are working with a very reactive metal. A reactive metal can react with water to release hydrogen gas. Okay, that is electrochemistry. For electrolysis, right, we also always consider participation of water. So that's why when it comes to electrolysis, if you refer to your data booklet, there's so many equations involving water. So which one should you choose? Okay, so for electrolysis, right, the first thing you need to check is, are we talking about a cathode or anode reaction? Okay, so if we are talking about a cathode reaction, then I hope you still remember that you need to look for water on the left side. Okay, so if you look at the data booklet given to you, right, there are several instances whereby water is found on the left side. So water with oxygen and water alone. Okay, so just now you weren't asked, so which one should I choose? So if I base it on the one that is more positive, right, then I should be choosing this as my equation. But please take note, for you to choose this as your equation, right, the question must describe presence of air, or air is bubbled into the aqueous medium. Without the term presence of air or air bubbled into the aqueous medium, then this is not present. So if O2 is not present, then you cannot choose this as your answer. Okay, so this is the one, the only choice, with water appearing on the left side. Okay, am I clear on this? So if you're talking about water at the anode, you need to look for water on the right side, because anode is where oxidation takes place. Okay, so if you look at water, right, so there is this here, this, and where else? Is there anywhere else? Nowhere else, right? So oxidation of water, so between these two, the reverse direction, okay, obviously the less negative one, or the more less negative one, the reverse direction, right? This one is more negative, this one is less negative. Yeah, okay. So the one that is less negative will be the preferred equation to use. Okay, so water on the left, right side is not so problematic, right? Yeah, the rest you need something else. Oh, so this is another equation whereby you have water on the left side, but that is in the presence of HO2 minus. Okay, so this is something that I never see before. I also don't know what that is. Okay, so it's never applicable. Okay, so let's quickly look at the answer now. Okay, so at the anode, so double check, anode is where is positive charge. So this means that it will attract the anion as well as water. So the species considered at the anode will be the anion sulfates as well as your water. Okay, so in this case, we are talking about oxidation. Therefore, the species must appear on the right side of the equation. So if you talk about the species on the right side, quoting their relevant E0 values, then you recognize that positive 1.23 is more negative. So therefore, it will be the one that is preferentially oxidized. Okay, so with this in mind, then I can quickly identify my anode reaction to be water. Okay, water being oxidized. Right, so this one is quite straightforward, right? Yeah. Any question? So you must see in the reverse direction. I'm also trying to get used to that. Okay, so let's look at part B. Explain why the gas volume are in the ratio of 2:1. Okay, now there are two ways of looking at it. Okay, one way will be coming out with an overall balance equation. Okay, so from the overall balance equation, right, you will see that there is 1 mole of oxygen and 2 moles of hydrogen produced from the overall equation. So using this, that can easily explain why the gas volumes are produced in 2:1 ratio by deriving the overall balance equation. Okay, or alternatively, you can say that for the same 4 moles of electrons transferred, okay, there will be 2 moles of hydrogen gas and 1 mole of oxygen gas formed. Also can. Right? So there are two methods. Okay, so what we have suggested here is the second method. For every 4 mole of electrons passed, I see that there is 2 moles of hydrogen and 1 mole of oxygen produced. Therefore, the ratio is as such. Yeah, okay. Right, then part C, state and explain the color of the litmus. So what is the color of the litmus at the cathode? What is being produced at the cathode? Cathode is where reduction takes place, right? So upon reduction, what is produced? Yeah, the OH minus. So if it's OH minus is alkaline, then it will cause your litmus to turn blue. Okay, so this is the thinking process. Then at the positive electrode, what is produced? H plus. So therefore, it will turn red. Okay, around this electrode. Okay, so this one is quite straightforward. All right, so let's quickly move on to the concentration of ions. So concentration, so remember there are three factors. Number one is the E naught value. Number two is the concentration, effect of concentration. And number three is the whether you are using a reactive electrode. Okay, these three factors. So we are done with the E naught value factor. Now we are considering the concentration factor. Okay, so in your syllabus, you need to recognize that when I replace a dilute sodium chloride solution with brine. Okay, what is brine? Brine is highly concentrated sodium chloride solution. Okay, so when I replace it with brine, then I can actually causes the E naught value of your chloride to change. And it will become the one that is preferentially discharged. Yeah, okay. So if you look at the products at the cathode, whereby you are considering the sodium plus and water undergoing reduction. Okay, so obviously the sodium plus and water, water is the one that is more positive. So therefore it will be preferentially reduced. Okay, so that one is logical. All right. And because of the large difference here, even though we pump in a lot of sodium plus, right, it will not be able to swap the ion that is being discharged. Okay, but in contrast, if you look at the anode reaction, okay, the oxidation of water versus chloride, okay, do appreciate that the E naught values are rather close. Okay, these E naught values are rather close. Okay, don't ask me how close is close. Okay, just know that in A-level syllabus, you need to recognize once I replace dilute sodium chloride solution with brine, I need to know that the anode reaction will change. Okay, chloride will be the one that is preferentially discharged. And why is it preferentially discharged? Because it has become more positive. Less negative. Okay, so in this case, the concentration, high concentration of your chloride here will cause this value, which is no longer under standard condition because this one is more than 1 mole per dm cube. All right, so this one will become less positive because it's the reverse direction, right? So it will become less positive. So when it becomes less positive, it means that it will favor the reverse direction more. Okay, so the position of equilibrium will shift to the left due to Le Chatelier's principle. It will become less positive. So the reverse direction will be more favored. Okay, so chloride becomes the one that is preferentially oxidized. Okay, so in syllabus, this is what you need to memorize. Any other cases, right? Any other comparison, it must be suggested by the question. Okay, if the question never say anything, right, then your assumption is the concentration cannot override. Okay, concentration is not able to override the difference, cannot breach. Yeah, only for this. So once your dilute sodium chloride is replaced with brine, then you need to recognize that anode reaction is different. Okay, and why has it become different? That is the Le Chatelier's principle. Yeah, NaCl, sodium chloride. NaCl, sodium chloride. Only for this. Yes. Yes. Okay. All right. So can we quickly look at this? Checkpoint number 2 on page 10. Are you done? Okay, first of all, you must identify where is the anode, where is the cathode. Yeah, so are you able to tell which one is the cathode, which one is the anode? After identifying the anode and cathode, then you need to consider participation of the different species. Huh? Yeah, even if it's concentrated, there's still water. Definitely. When I talk about concentration, concentrated sodium chloride is just higher than 1 mole per dm cube. Yeah. How much higher, I'm not sure, but then it's definitely more than 1 mole per dm cube. Okay, so where is the cathode, where is the anode? P is the cathode at the anode. P is the anode. Huh? So P is the anode, while this is the cathode. Okay, so for the cathode, it is still water undergoing reduction, right? To form your OH minus. Right? Okay, where the anode, for the anode, what is being oxidized? The chloride will be the one, right? Because it has become less positive. Cannot get it. Okay, so I shall write this chlorine in equilibrium with chloride. Okay, so it will be that word. So the E naught will become less positive. All right, so when the E naught becomes less positive, it has a greater tendency to be oxidized. So in this case, your chloride will become oxidized to chlorine. Okay, so chlorine, right? How will it react with the litmus paper? How will the chlorine react with the litmus paper? Yeah, it will bleach it. So litmus paper will become white. So in this case, right, and for the anode, which is P, it will become white. Why white? It's because you are talking about the paper soaked in the litmus solution. So the litmus solution itself is actually colorless. Okay, so the apple is the answer. Why is it blue? Because of the alkaline that is produced. Can? So far so good? Okay, quite straightforward, huh? Okay, let's move on to the next part. Any question? Okay, let's look at the third factor, nature of electrodes. So if we are working with inert electrode, then we don't need to consider their participation. But if we are talking about reactive electrode, please appreciate that electrode can only take part in oxidation in the anode reaction. Okay, so if we are talking about cathode, right, you don't need to consider participation of the electrode because metal cannot be further reduced. In contrast, at the anode, the metal electrode can be oxidized. All right, so you only consider participation of the electrode at the anode. Okay, you can ignore its presence at the cathode. It doesn't make any difference. Okay, so this is some example that is given. I will not go through this. Okay, this one you can read on your own. So let's try the checkpoint 3. Huh? Because metal can only be oxidized. Metal cannot be reduced. Cathode is where reduction takes place. It's a bit hot here, you know. There's no aircon. It's just feel warmer here. Oh, careful, careful. Javin, you're not feeling well, is it? You look very tired. Huh? You're okay.
NO3 minus, right? All the equations involve hydrogen, but then we're not given.
H plus.
Yeah, sorry, H plus. We're not given acidic medium.
Yeah.
So how can we consider any of these equations?
Not applicable. So you're talking about anode. Anode nitrate should be on the right side. If it's anode, right? Then do you have nitrate on the right side?
No.
Then you shouldn't consider nitrate. Anode is attracting anion, right? Anode is where oxidation takes place.
We can just like flip.
No. I never teach you flip. I always say anode oxidation species must have the right side. We never flip. I never teach you flip. I never ask you to flip.
If we were to consider water on the right hand side, then you say the species must be present. Is it only the species on the right hand side must be present?
Yeah.
So like you don't like if between this and this, then in what
The one that
circumstance?
is more, because you are trying to oxidize it, right? So the one that is less positive will be the preferred one.
So in what circumstance will you even use this?
No one.
You would never.
Because when you look at water on the right side, right, this one is the one that is less positive.
So wait, is it like you must have H2O2 on the left hand side in order to consider this?
Yeah. Half cell lah, if you're talking about half cell. If I tell you that this half cell is made out of water and hydrogen peroxide, then you have to use this.
So if you're only given water,
yeah,
then it can undergo both because
at the anode, water will undergo oxidation. Therefore, water must be on the right side. So there are two equations with water on the right side. So you choose the one.
Prerequisites.
Yeah. Okay, are you done? Can I go through the answers? Can I go through the answers? Because if not, your friend will be doing something else. Yeah, okay, so let's go through the answers. So for the first one, it's quite straightforward. You are just talking about molten salt. Okay, so molten salt, you don't even need to consider the presence of water. You just consider the cation and the anion. Okay, so the species involved will be obviously the barium 2+ and your chloride minus. Okay, so cathode is where reduction takes place. Remember, this is where reduction takes place, and it is a negative polarity. So it is only able to attract barium 2+. So you will just need to consider reduction of barium 2+. Okay, in contrast, for the anode is positive polarity, so you will only attract your chloride. So therefore, you only consider oxidation of chloride, and the answer is straightforward. Okay, so let's look at part 2, dilute sodium hydroxide solution. So in this case, you have to recognize that there's aqueous medium, so you need to consider sodium plus, hydroxide, and water. Okay, so remember, you only consider OH minus or H plus, provided you are working with alkali or acid, respectively. Okay, if it's just aqueous medium, you should only consider water, not H plus, not OH minus. Okay, I hope I'm very clear on this. Alkali is present, therefore I consider OH minus. Acid is present, therefore I consider H plus. If no acid, no alkali, only consider water. Okay, in aqueous medium. So same thing. This is a negative polarity for cathode. Okay, so you attract the cation and the water as well. So between these two, there's two possibilities: reduction of sodium plus versus reduction of water. So obviously between the two, the one that is preferentially reduced will be the one that is more positive. Okay, so water will be reduced. Quite straightforward. Okay, then the anion here, right? For the anode, we are considering oxidation. So it will consider oxidation of hydroxide and oxidation of water. So between these two, which one will be oxidized? Which one will be oxidized? Hydroxide. So this will be the preferred equation. Then let's look at the part 3. silver nitrate aqueous. So what are the species present? That will be your what will be the species present for silver nitrate aqueous? Pardon again, sorry. No, we are showing what is happening at the anode. And what is happening at the anode is oxidation. Yeah, when you code values to make comparison, is by default reduction process. Yeah, anode is oxidation. So I'm showing oxidation. Yeah. Okay, so let's look at silver nitrate. What are the species present? The silver plus nitrate and water, right? So for the cathode, which is a negative polarity, it will be able to attract your cation as well as water. So between silver plus and water, which one will be preferentially reduced? Yeah, Ag plus, because Ag plus is a positive 0.80 volt, right? Whereas your water is a negative value. I can't remember this. Okay, so I know that this is the answer. So for this, another one, the anion, nitrates, and your water. Remember, this is where oxidation takes place. Positive polarity attracting the anion. Okay, so this means that nitrate must appear on the right side. Do you ever get nitrate on the right side? Don't have, that's because nitrate is already a +5. There's no way you can further oxidize a nitrogen +5 to something else. Nitrogen is a group 15 element. Maximum oxidation state is +5. Cannot go beyond. Okay, so that's why your nitrate cannot appear on the right side. Okay, so this means that this is not applicable. All right, so therefore you can only consider oxidation of water to become your oxygen and H+, right? Okay, so that's the half equation you should choose. Yeah, then let's look at part B. Sulfuric acid using copper electrodes. Okay, so now we are no longer using inert electrode, we are using a reactive electrode. Okay, so at the cathode, which is a negative polarity, you should be considering attraction of H+ and water, right? Do I need to consider copper at the cathode? Copper metal cannot be further reduced, so you don't need to consider copper at cathode. Okay, so between these two, which one is preferentially discharged? Yeah, H+, right? Okay, I hope you can see that H+ will be the one that is preferentially discharged. Okay, whereas for anode, what do you think will happen? Anode, positive polarity, it will attract your sulfates. Okay, it will attract your water and plus your reactive electrode copper. All right, so these are the three species that you need to consider at the anode. All right, so which one is preferentially discharged? No. Now remember, sulfate on the right side will come from S2082 minus. And this E0 value is a positive 2.01 volt. Isn't this 2.01 volt? Yeah. Whereas water undergoing reduction is a E0 1.23 volt. Then copper to become copper 2 to become copper, E0 is a positive 0.34 volt. So between these three, right, which one is the preferentially oxidized? Which one? CO2? Cu? Copper, you mean? Copper will be preferentially oxidized, right? Remember, you are talking about anode, you are talking about species on the right side. Species on the right side. Sorry. Yeah, species on the right side. Okay, so this will be the one that is preferentially oxidized. These are all the half equations. Are you able to find all the half equations? Yeah, can, right? Yep. Q plus plus. Consider. But then because we are talking about oxidation. So we should choose the one that is less positive. I mean, you can consider this, but the conclusion is still the same. Yeah. Okay. Any other question to clarify? I lazy to show you all the half equation. Can? Okay, let's move on. Okay, so for the next part, right, is more of the calculation. Okay, so basically there's a few equations that you need to learn. Okay, number one is your Faraday's constant. Okay, for those who are taking physics, I think you have learned this term before, Faraday's constant, right? Faraday's constant. Okay, so you can find this value from your data booklet is a 96500. Okay, so basically it's giving you the total charge carried by 1 mole of electrons. Right, so Faraday's constant tells you the total charge carried by 1 mole of electron. Okay, so L is your Avogadro's number. So 6.02 times 10 power 23. Avogadro's number. Okay, you don't need to memorize this. This one you can get from the data booklet. This one can also be obtained from data booklet. Yeah. Okay, so quantity of charge passed during electrolysis, right? The rest you can read on your own. Okay, so the relationship, there are two equations that you need to apply. The first one is Q, which is the total charge, equals to number of moles of electrons times Faraday's constant. Okay, so this particular equation over here, right, is referring to the charge required to discharge your anion, to discharge an ion or water. Okay, so it's the total charge required to discharge your ion or water. So this means that you need to determine the moles of electrons from the half equation as well as the moles of ions or water involved. Okay, so to apply this equation, you need to make reference to the half equation. And you also need to calculate what is the number of moles of ions or water that is involved. Okay, so this one is the mole of electrons. To determine the NE. Right, so there's another total charge which can be calculated from the battery that you use. So if you are calculating the total charge supplied by your battery, it will be Q equals to IT. All right, so technically, whatever that is provided by your battery should be used to discharge the ions. So therefore, we end up with this relationship. They should be equal. Okay, electricity or electrons provided by your battery should be equals to the charge required to cause your ions or water to discharge. Okay, so this is what is happening over here. So the rest, I will not go through with you. It's just work example, some calculation. So let's go straight to the checkpoint 4. Okay, so just remember that equation and know how to use it. If you're not sure on how to start, you can go through the work example first. Okay, I think for those who are not so familiar, right, because you don't do physics, what you can do is you can look at the data that's relevant to your battery, IT. Look for the current, look for the time. That is electricity provided by a battery. So identify that as one set. Then the other set is the number of moles of electrons required to discharge your ions. So that is your number of moles of electrons. Okay, so look at the information that is relevant to that. You categorize your data, then it will make the calculation more straightforward. Learn to categorize the data. What is relevant to the battery? What is relevant to your species? After that, it will be clearer. Okay, so for this calculation, you only need to remember IT equals to NF. That's it. You're not using calculator, then keep your handphone. Okay, so how do you work through this? So as indicated by the color here, so IT is your current. So this is related to your battery current and the time. So this is for you to calculate. All right, and please take note, the time is by default in seconds first. You need to work, when you work out the time from here, right, it will be by default in seconds as your units. Okay, then later on, you need to convert to minutes. Okay, so that is your IT. So if you look at your NF, F is a Faraday's constant, which is 96500 obtained from your data booklet. So you need to work out what's the number of moles of electrons. So how do you work out the number of moles of electrons? Based on the equation. So based on the equation, chromium 3 plus has to accept 3 electrons in order to be reduced to chromium 0. Okay, so that will be 3 moles of electrons. But what is the mole of chromium deposited? 125 divided by 52. All right, so this is how we calculate the total mole of electrons from the mole of chromium times 3 of the electrons that is used to discharge it. Okay, then I substitute into the expression NF. Okay, so my I is 200 ampere. Time is for me to calculate. Then is equals to 3 times 125 divided by 52 multiplied by your Faraday's constant. Correct? Then are you able to calculate the time? Yeah, so when you convert to minutes, it should be 58 minutes. Can I? Okay, so the trick here is to categorize the data related to battery, categorize the data related to your chemical equation. Yeah. Can? Then the next part is something similar. Okay, so this one you can read on your own. So let's look at checkpoint 5.
So it's sorry, not an E, but it should be one more of. Do you say electrons discharged in Cr3 plus? Is that how you describe it?
Yeah, this is the total charge required to discharge your ions or water.
What I did was I just took one times.
One.
I took one more. Sorry, time taken to discharge 1 mole of Cr3 plus to Cr, right? Times number of moles. So I just wanted to know how to phrase this. So can we say time taken for 1 mole of Cr3 plus to be discharged?
Oh.
Is that the correct way to say it?
How do you calculate the time then?
Oh, I just treat this as 3 rather than 3 times this.
Oh, because it's per mole.
Yeah.
Yeah.
Just the phrasing. So time taken to discharge 1 mole of Cr3.
So will there be any change in the mass? So remember, electrolysis is not a spontaneous reaction. Whatever that is taking place is driven by your electricity. Yeah, so this means that as long as the total charge provided by your battery is the same, then the mass deposited should remain the same, despite initial concentration of your electrolyte. Okay, so this is something that you need to learn from checkpoint 5. Okay, so being non-spontaneous must be driven by the electricity provided. Okay, so do recognize that using the same potential difference or using the same currents and the time duration, the number of moles of electricity, electrons provided is the same. So as long as mole of electron provided the same, how much your ions discharged should remain the same. Because it's driven by electricity. Can make sense? Okay, so this is what I said just now. The reaction is non-spontaneous. It can only take place driven by the battery. Okay, so the moles of ions or water discharged depends on the moles of electron provided by your battery. Okay, independent of the initial concentration. Okay, of course, that is provided that the initial concentration is not limiting. Okay.
this concentration of the
Uh-huh.
it's not fair.
No, as long as it's not limiting. So you see the change here, right, is I'm making more concentrated. Yeah, so it will not be limiting. As long as it's not limiting, then whatever that's formed will be limited by the electricity provided.
Excess and increase in concentration would that affect like would it increase your reactions? This is triggered by the
Yeah. The question is not asking about rate. Yeah. Because rate of reaction can be enhanced if you use a bigger current. Yeah. Can? Any question to ask? Okay, so the rest you read on your own, can? Right, because you need to revisit this when you start your tutorial. Okay, so let's look at question 4. Now, there are 2 applications required in the syllabus. One of it is anodization of aluminium. The second one is purification of copper. Okay, so in anodization of the aluminium, right, basically what we are doing is we are trying to increase the thickness of the protective oxide layer, okay, to protect the aluminium electrode or the metal itself. Okay, so anodization, blah, blah, blah. This one you can read on your own. Okay, there's only one thing that I want to highlight. At the anode where your aluminium is, okay, so in this reaction, right, because of the term anodization, so naturally, I need you to associate aluminium as the anode, while the platinum is the cathode. Okay, and at the anode is where oxidation takes place, right? This is the overall equation that is taking place. But if you look at the side note, right, the oxidation is actually a combination of 2 reactions. Reaction number 1 is oxidation of water to form oxygen gas. Okay, so that's reaction number 1. Then reaction number 2 is the oxygen reacts with the aluminium metal to form the aluminium oxide. So that is the protective layer. Okay, so what is shown at the anode reaction is the overall reaction already. Okay, but do recognize that it's a combination of 2 reactions. Okay, so in anodization, it's typically taking place in the acidified medium. Okay, so this one has come out in A-level question before. So do appreciate that it's always an acidified medium, not an alkaline medium. And I'll explain to you why using the checkpoint later on. Why must we not use an alkaline medium? It must definitely be an acidified medium. Okay, so this is something that you need to know how to describe. Okay, you must know how to describe the process of anodization. Okay, all right, so the rest you can read on your own. Second application is purification of copper. All right, so can you tell each other why do I let the impure copper be the anode while cathode is the pure copper? Why so? Tell each other. Can I swap? Why not? Why must I make the impure copper the anode? What do you think? And you must know, okay, anodization of aluminium, anode is the aluminium. Straightforward. But this one, why must the impure copper be the anode? Think about it. There's logic behind. Anyone? Why must the impure copper be the anode? Yeah, you must make it dissolve. Yeah, because in the impure metal, the metals are mixed together. The only way to separate them is to oxidize to release as cation ions. Okay, that's why the impure copper must be the anode. You need to oxidize it so that it becomes cation and release into the solution. Okay, then the cathode must be your pure copper because that is where your copper 2 plus is deposited. Correct or not? Make sense? Yeah. So if you remember this, right, please take note. Okay, so this is what we have just discussed. Impure copper as the anode is important because you need the copper to dissolve to give the cations in order to be separated from other metals. Okay, and cathode is where copper 2 is deposited and reduced. Make sense? By dissolving it, we are trying to break it up. That's how you can purify it. Okay, then and second thing I want you to take note of, right? Because of the need to dissolve your copper metal in the impure metal, right, to become cations, the potential difference supplied by the battery must be sufficient to oxidize your copper. Okay, so in other words, any metals that can be oxidized above copper will also be released as cations. Agree? Right? You cannot control what is found together with your impure copper, right? So any cations or any metal that is more reactive than your copper will also be oxidized in the process. Okay, so the recognition that copper must become copper 2 plus is important. No, when they are more reactive, then they are less likely to be reduced at the cathode also. Yeah. More reactive means that they tend to stay in the cation form than to become metal atom. Right?
So you still largely only form your
Copper 2. Copper 2 reduced to copper 0.
So the stuff that like the other metals that oxidize.
I will go through that. Yeah, I'll go through that. So are you done with this part? You understand why I bring this up? Okay, so with this in mind, right, if you look at the metals that is present in your impure metal, they are copper, zinc, iron, silver, and gold. Right, you have gold inside. Okay, so in this case, right, please take note. If you look at the copper 2 reduction potential as a reference, right, obviously zinc and iron are more reactive. So therefore, they are also oxidized to become the respective cations together with your copper. Okay, while on the other hand, your gold and silver are more inert. They will not be oxidized, so they will drop down below the electrode as sludge. So they will remain as metal. They will not become cations. Okay, so they will disintegrate and be deposited below the electrode as sludge. All right, so the cation that is released into your solution, zinc 2 plus, iron 2 plus, and your copper 2 plus. So remember, at the cathode, we should be choosing the one that is more positive E naught to be the one that is preferentially reduced. So if you look at the E naught values of your zinc 2 plus, iron 2 plus, and copper 2 plus, this one is the most positive. So at the cathode, copper 2 plus having the most positive E naught will be the one that is preferentially reduced. So no issue at the cathode. And also do appreciate that because we are talking about impurities in copper ore. So this means that majority is copper. The other metals are present in trace amount. So the concentration of your zinc 2 plus and iron 2 plus is actually very low. So the chance of it undergoing reduction at the cathode is also less likely as a result. Okay, so that is how it works. Ken? All right, so if you are able to understand, you are required to know how to explain how it works by quoting the relevant half equations and the E naught values. Okay, so this is required in your syllabus. Okay, so let's quickly look at checkpoint 6. After we are done with this, I will release you. It's almost done. Okay. 5 minutes left. Sorry. Okay, so let's quickly look at checkpoint 6. Actually, the answer is quite obvious. Right. You have your notes with you, you know what's the answer already. What's the answer? Yeah, apple. Okay. So I just want to ask, what's wrong with B? Can you explain that? What's wrong with B? This one I don't know. In geography, do you learn refining of aluminium from aluminium oxide? Bauxite. This one. You learn this? Previously in JH, do you learn this? Purification of aluminium from aluminium ore. No impression. Okay. So this one is not applicable because you never see this before, of course. Then the Denmark cannot be the answer. Why? What's wrong with Denmark? So in this case, if you want to protect your aluminium, then you should be coating it with a more reactive metal. So we label this as a sacrificial layer. Have you heard of this before? Yeah, okay. So this one is not correct because you should use a more reactive metal. Okay, back to my question. What's wrong with option B? What's wrong? Okay, remember, to form the aluminium oxide layer, which is the protective layer, I need to produce oxygen, right? Then oxygen is the one that oxidizes your aluminium to form the aluminium oxide. So the oxygen is coming from water, all right? So when I change the electrolyte from water to sodium hydroxide, does it mean that I can no longer form oxygen at the anode? Does it mean that? Don't stare at me, look at the data booklet. Can hydroxide be oxidized to give oxygen at the anode? Can or not? Can. And in fact, it has a greater tendency than water to become oxygen, right? Do you notice that? Yeah. So, then what's wrong? Hydroxide can also give oxygen, and some more is happening more readily, has a greater tendency than water to be giving you oxygen upon oxidation. So why don't I use hydroxide? What's wrong? What's wrong? What do you think? Yeah. So that comes to the, why do I emphasize acidified medium? Why can't it be alkaline medium? So what's wrong with alkaline medium? What's wrong? Reaction cannot occur, but we just say that hydroxide can also be oxidized at the anode to give oxygen. And oxygen is the one that forms the aluminum oxide protective layer. So why can't I use hydroxide? Even though it can also give you O2. E cell, but there's no E cell to calculate here. It's driven by the battery. E cell is only relevant if it's electrochemistry. to check whether the reaction is spontaneous or not. I don't need to calculate E cell in electrolysis topic. You look at this whole topic, are you asked to calculate E cell? No, right? So what is it? What do you think? So why must anodization of aluminium take place in acidified medium, not an alkaline medium? Aluminum hydroxide. So it's still an oxide layer. Now remember I say that hydroxide can be oxidized to give you O2, and O2 is the one that forms the oxide layer. So O2 need not necessarily come from water, it can also come from hydroxide. So what's wrong with hydroxide? It's related to your inorganic QA. Aluminum oxide is soluble in what? Excess of alkali. Why? Yeah, so Al2O3, right, is amphoteric, is able to react with the hydroxide to form the aluminate. Yeah, so it will dissolve the oxide layer. So as the hydroxide reacts and be attracted to the anode, right, it will dissolve the oxide layer as well. Okay, then you're wondering, wouldn't H plus dissolve your aluminum oxide as well? But then you remember, H plus migrate to your cathode. Hydroxide migrate to your anode. So there's a high concentration of hydroxide at the anode. Okay, I repeat myself. H plus travel to your cathode, while OH minus travel to your anode. So high concentration of hydroxide at the anode, right, will dissolve your aluminum oxide layer. Hence, the oxide layer cannot be formed on the aluminum object. Can? Right, so if there's no further question, then we'll end the lesson today. Okay, unfortunately, it's right on the dot. I cannot release you earlier.